turn that on now. And now that it's recording, maybe I'll even say welcome like one more time. Welcome everyone to the first Friday Math Seminar at Bard College at Simon's Rock. We're so happy to introduce Professor Kaethe Minden, who will speak with us today about infinite Latin squares. So take it away, and thank you so much for presenting today.
Thank you, Ken, for the great introduction, and thank you everyone for coming. I'm happy to be here. It's very exciting. And yeah, I mean, this is, you know, while I have been having to teach remotely more and more this semester, it's still not completely smooth for me. So I do want to apologize in advance for any, you know, difficulties in that regard, technical difficulties and stuff like that. It might be a little bit clumsy going. So anyway, yeah, so and also please interrupt me if you have questions throughout the talk, and just interrupt and shout at me or something like that. And this is meant, you know, I would like to, I'll be asking questions throughout the talk anyway, so feel free to unmute yourself and let me know if you have any questions or comments. So yeah, so this is a talk based on a paper that I wrote with these three people, Anthony Evans, Gage Martin, and Matt Allis. It's kind of an interesting story, I guess, how it came to be. So Matt Allis is he was a professor at Marlborough College. Now he's at Emerson. And Gage Martin was a student of his and asked this question about infinite Latin squares. So Matt Allis works with combinatorics and with Latin squares and group-based stuff, group-based combinatorics. And Gage had this question and they were able together to answer quite a few things, or at least get some partial results. I joined Matt at Marlborough College for 2 years. And he was like, oh, you're a set theorist, you know stuff about infinity, so maybe you can help us with this paper. And it was really fun. Yeah, I looked at the paper and I had some things to add to it and some ways of presenting it in a certain way with infinity. And it was really fun working on it. And I was just like, yes, this is great. I never thought I would be doing combinatorial type stuff. And, you know, set theory is often way off over in another area, and so it's nice to have this like connection to the finite, I guess, in Latin squares. And then while we were working on it, we had some questions about group-based combinatorics type stuff, and so we just emailed Anthony Evans kind of out of the blue because he's sort of an expert on some of these things we had questions about, and he produced some results as well and was happy to work with us on that. So it's sort of interesting how collaboration can work, where you can get all these people working together when I haven't really met two of them. And I mean, the order that the paper where we wrote the authors was really just in alphabetical order. And I don't know that that reflects any amount of the work. I think we all contributed sort of there, but I think in math, often you don't have like first author, second author, you know, meaning anything specifically. So that's just some comments on that for what it's worth. Okay, so to start off, I was just gonna basically motivate and introduce what a Latin square is, and motivate and introduce different types of Latin squares, and then talk about generalizing it to the infinite as we did in the paper. So let me just go to this first slide. All right, so here we have a square. Okay, so let's say that this square is representing a plot of land, say, that you have in your backyard, or I don't know, you're a farmer, and let's say that you have 4 different types of crops. So now I'm gonna write this over here, 4 types of crops. Say you have, I don't know, squash, beans, corn, and onions. Okay, and you'd like to test their viability in this plot of land that you have. You want to see which of these do the best in growing on this soil. So can anybody suggest a way of partitioning the square into 4 parts so that I can test each of them and how they I'm just drawing little symbols. I don't know if I can see if you're raising your hand, so just shout. Just unmute yourself and tell me if you can think of a way of partitioning the square.
Well, why don't you just make like 4 stretches of land going, I don't know, horizontally, and plant one thing in each stretch of land?
Like that? Sure, yeah. So that would totally work. Yeah, so let's say that I'm gonna label them with numbers because I do math and I like numbers. So I'm gonna label squash as 0, beans as 1, corn as 2, 3 as onions. So we could just plant our squash up here, then our beans, then our corn, then our onions. Any other suggestions?
I think you can divide it vertically as a half,
Sure.
and then horizontally as a half.
Nice. Yes, so I'm going to erase what Miha suggested. Sorry, Miha. Maybe I'll keep it like this. But actually, I can go to my next slide because I think the way that you suggested is what's on this next slide. So I should probably clear then and erase these lines so that you can see what that is. So is this what you were suggesting,
Yes.
Evelyn? Cool. Yeah, so that's another way that we could break it up. I mean, there's lots of ways of doing it, so we don't have to spend too much time going into that. But so let's look at this one. This is the way that I also thought of breaking it up, Evelyn's way of doing it. Now, I've kind of lied to you. I mean, I didn't lie to you. I just didn't give you all of the information, maybe. So this is a plot of land that you have, but it's not just in this blank page of space and stuff. It's in the context of your yard or a location. And what I failed to tell you is that actually there's a river along this side of your plot of land, okay? So now do we still like this way of arranging our crops? I mean, is it really gonna give each of the crops a fair play here at which one is gonna do the best?
No.
No, yeah, so why not?
Like 1 and 3 is far away from the river, so it will not like get a fair water.
Exactly,
like.
right?
Yeah, yeah.
Yeah, it could be that the only reason, the only reason that squash does so well is that it's right by the water, right? And that normally it wouldn't do so well on this plot of land. Or it could be that, you know, beans would normally do well if they got a little bit more water. Okay. So can we think then of how we could arrange ourselves to a little bit better so that they each get a good amount of water? How we could arrange the crops.
Use my thing. Use the thing I said.
That's true, right? The one that Miha suggested would actually have worked better in that situation, right? If we arranged it in these horizontal things. But Miha, I'm sorry, I also lied. I mean, I forgot to tell you a little bit more about this plot of land, right? I mean, I keep hiding some information from you. So actually, as it turns out, this is just there's actually a road up here on this top part of the square. Okay, so I mean, so maybe we don't want to arrange it like this. right? Can we see what the problem is with if I have it like this? It could be that squash now does really badly or maybe really well just because it's right up against the road. And so you can imagine that you have this on maybe all of the sides. You have some different sort of phenomenon that will make it so that you kind of want to distribute your crops maybe a little bit more balanced, in a more balanced way. So let's see, I'm going to erase these. Any suggestions as to now what I can do?
Break it up into 16.
Right. So I can break it up into a bunch of squares. Like this, Bob?
Like that. Perfect.
Exactly. Right. So now I have on the top part the four different crops. On the side, I have 4 different crops. And on all of these sides, and I've done this. And this is exactly motivating a Latin square. So we've seen here that oops, didn't mean to go to the next slide. We've seen here that we've produced a square such that in each row and in each column, each crop or each number appears once, right? Exactly once. So each crop appears exactly once in each row or column. Has anybody sort of seen, I mean, maybe this is too soon, you can think about it, but I mean, something like that where every number appears exactly once in each row or each column. Does that sound familiar to anyone, or is there another square like that that you've seen where this pattern happens?
Addition mod 4.
Addition mod 4, nice. Yeah, there you would have 0, 1, 2, 3. So we'll get to that being more relevant.
Wait, in the chat we're seeing Sudoku.
Sudoku, nice. Yes, that's what I was thinking of as well. Is like you have that in Sudoku, except in Sudoku you have the further requirement that each of these in each of these squares you have each crop appearing exactly once, for example. Okay, so that's a Latin square. So this is one example, and Sudoku would also be an example. And you can kind of see already if you've taken group theory or anything that this looks like an addition table, mod 4, as Bill pointed out. Now, okay, so there are some issues now with if I'm really trying to test these crops, because I've in the way that I've set it up, at least I've randomly sort of distributed them, so to speak, right? So at least each of them will be on all of these sides. But one thing that I'm noticing is that with the way I've done it, crop 2 seems to always be next to crop 3 like this. So corn seems to always be next to onions. Okay, so if I imagine that maybe sometimes of the day, the sun is in this sort of top corner in such a way that it's maybe the corn is always blocking the onions or something like that, that maybe this isn't exactly how I want to set myself up. So, right, if the sun's sort of up here, 2 is always blocking 3. So a further requirement that we might ask of a Latin square is that we don't have this happening. We don't have that 2 is always next to, that 2 is more than once right next to 3. So we could ask the same, you see the same thing happens with 1 and 2 and with 3 and 0 in those orders. So any ideas to what I can do? Like, I mean, you can work that on your own a little bit. Like, is there an arrangement that I could have done then to avoid 2 always being next to 3 like this? Yeah, maybe that's, I think it turns out that if you just swap columns, the second 2 columns, I think something like that will work. But certainly another possibility would also be, I think, what I have on the next slide. So here, do we have 2 and 3 always next to each other? No, I only see 2 next to 3 like that this one time, right? And you can verify that, oops, that happens. For all of your numbers, so this is an example of what we call a Roman square. A Roman square is what we might also call row complete. So every crop appears in adjacent plots at most once in every order. So you have this nice neighbor balance where it's not the case that you always have 3, is before 1 in every single row. You have a nice balance of, well, sometimes 1 is before 3, sometimes they're really far away like this in different orders. And you have this nice randomization.
Can you say the definition again?
So the definition would be that every number, every crop appears in adjacent cells or plots at most once in every possible, in any order, right? So order matters here. It's okay that the 1 and the 3 are next to each other like this twice. Okay, it's just that they're in different orders. That's what makes it okay. So it's not like we're going to be in a situation where 2 is always blocking 3. It only blocks it in this one row, in the second row. Right, so I can write that down.
And you need to check both rows and columns?
Not for Romans. So,
Okay.
oops, did I just go too far ahead? I should still be on Roman. Sorry, I keep like hitting my mouse in a specific way and then it jumps ahead and gives everything away. But for a Roman square, we just want it to be row complete.
Oh,
Which is just that
right.
I'm trying to make my pen less thick and it's not. Oh,
I
here we
see.
go.
So you can, is it possible to be both row and column complete?
Great question, right? So we've noticed, so maybe you've noticed already that, and I'm not going to finish writing that down unless somebody wants me to write down the definition for Roman, but it looks like Lauren has noticed that already in this Roman square, I don't have that for columns, right? 2 seems to always be above 3 here, right? And so this is column complete. This is not, this fails to be column complete, this example, right? So row complete was each crop appears in adjacent plots at most once in each order. Okay, so in fact, I think there's a name for a square that's row complete, but not necessarily a Latin square. And that's called, I think, Tuscan. So the Roman part of it is that it's also a Latin square. But anyway, there's all kinds of fun names for these things. But since they sort of came up, there's probably a name for the other thing. But the thing that I'm also concerned about, other than Roman squares, is making sure that it's also going to be column complete in this sense. And we call the square that is both column complete and row complete in every possible way and for every possible distance. So with row complete, we're only concerned about adjacent plots. But what we want is really for it to be at every possible distance, like maybe even just being 2 away every time is a problem. And so at every possible distance, if you can find a square that has that property, we call it a Vatican square. And this would be an example of a Vatican square for this 4x4 square. Okay, so here, for every possible distance, we only have those combinations at most once. So it's as balanced as possible in rows and columns at all possible distances. So I think of this as a kind of neighbor balance criterion, the row completeness and the column completeness. And Vatican squares are just as balanced as possible with our crop distribution. Okay, so that's what a Vatican square is. Now, Bill already pointed this out earlier a little bit about the square that we had before, but maybe we can look at this a little bit. I mean, what kind of symmetries are we seeing? Are there anything, I mean, what kind of other nice properties does it look like we have in this square? So we have this nice neighbor balance, but when you just visually look at it, I mean, does anything strike you as, does anything pop out at you at a nice property of it?
Diagonals.
Yeah, exactly. The diagonals are kind of nice. Right? I just have zeros along this diagonal and 2s on this other one. What else?
Well, if you look at the bottom triangle and you flip it and reflect it, like the bottom triangle is sort of a reflection of the top triangle, but flipped.
Nice. Yeah. It's sort of like reflected in both, along both of the diagonals.
Rotated.
Or were you thinking of a different one?
No, that's what I was thinking. Rotated is a good word for it.
Like anti-symmetric.
Like here too. Right, so along any of these like triangles. Yeah, so yeah, and so noticing this kind of thing tells us that this whole thing, I'm gonna delete all of the context about that, but those symmetries exactly tell us that it comes, you can see maybe more clearly when I color it how I came up with this square is that I basically made a group table, an addition table, let's say, for Z mod 4, right? So if I think of the elements of Z mod 4 as just, you know, well, they're just 0, 1, and 2, 3.
So
Mm-hmm.
this makes me wonder whether this property is only available for evens.
That's a really good question. Yes. So yeah, I mean, it seems like you can, yeah. So asking a question like that is exactly the kind of thing that comes up when you look at these finite Vatican squares, right? So what's happening here is that I'm just counting by 4. So I have 0, 1, 2, 3. And then when I go to 4, it goes back to 0, 5 goes to 1, 6, 7, and so on. I'm just counting by 4s here. And so all that's happening is that to produce all these black numbers, I'm just adding the value in that top row to the first column to get this. And then I'm taking it modulo 4, so to speak. So I'm going back, I'm sort of cycling back over there. Okay, so as it turns out, to produce this Vatican square, all that I really needed to do was just to say this top row. And then I can generate the entire rest of the square. So if I just give this top row, how do you think, I mean, what does it look like? How do I get this first column?
You just
Well,
switched 1 and 3.
So I switch 1 and 3, and then I have 2, nice. And it turns out that in Z mod 4, that's just going to be equivalent to taking a sort of additive inverse. So what I'm really kind of doing is subtracting 3 from 4. I'm subtracting 1 from 4 to get 3, and I'm subtracting 2 from 4 to get 2, right? So yeah, so just given this first row, I can then generate the rest of the squares. So we like finding these nice sequences, and these are called terraces. Because, let's see, so is it the case that I could have just used anything for that first row? It's not. So let's say that I wanted to make the square with 0, 1, 2, 3. What would be my first column then? Oops, I just gave it all away.
3, 2, 1.
Right, exactly. It'd be the
No,
opposite.
but is this is assuming you want to have those diagonals and stuff, those properties?
Yeah, so this is just generating, just so that just from this first, just from one sequence of numbers, I can generate the entire square in a canonical way, right? This is how I want to be able to build Vatican squares in general, is just from any sequence to canonically build the square. And so, yeah, so if I go with the method that I outlined in a little bit in the last slide, this is what I would do. I would have 3, 2, 1 instead of 1, 2, 3 on the first column. And then I would just add them and generate the square that way. So I do get this nice symmetry with the zeros along, right? And it works, but does this end up being, is this actually a Vatican square?
No, it's not real
No.
complete.
Right, it's not balanced, right? It's not real complete. So for example, right here, we have these 2s and 3s always next to each other. So this isn't a Vatican square. So it turns out that with Vatican squares, as I was saying, like basically we can generate them pretty canonically just using very carefully crafted sequences, right, that are essentially, in this case, elements of our group, so to speak. We can then produce the whole square that way. And it turns out that you do get this sort of equivalence. And to answer Lauren's question, you do get Vatican squares for all orders that are of the form p minus 1, where p is prime. So that'll be on a later slide, but the even thing is definitely clever. And it's all about building these things called terraces. It's all just basically coming up with terraces. And then of course you can generate tables in different ways. So there's maybe more, but for example, for p prime, you can get one for p minus 1 using the method that I outlined right here. Okay, so now I want to talk a little bit about the infinite. Okay, so we have all this stuff that we know about Latin squares, Roman squares, Vatican squares, and the question came up, well, what if I just grow this square? What if I take my elements not just from a finite set like 0, 1, 2, 3, but what if I have infinitely many numbers that I'm working with, maybe coming from the reals or maybe coming from the integers? So maybe I just have like an infinite number of crops with an infinite amount of soil or something. So then what kind of stuff happens? Does the same thing happen? Do you get this nice way of finding squares? And first of all, I guess let's just think about what's happening. You can get a Latin square pretty straightforwardly. So here's an example of an infinite Latin square, so to speak. If all we want is that in each row and column, each number is only appearing once, right? Then it's not too hard to generate a sort of integer square, kind of like this. So this would be one example of an infinite Latin square. So Latin squares aren't themselves too hard to build, but the question came up as to whether we can build Roman squares, Vatican squares, and all of this kind of stuff, or Sudoku puzzles like that are infinite and stuff. And what we managed to show in the paper is that yes, you can. So here's the result that I was saying earlier. So Vatican squares are known to exist for orders p minus 1. using terraces and Kaethe tables as outlined. So Kaethe tables were those addition tables that we had, and the terrace is that first sequence. And we were able to use the same basic methodology to do this for infinite, potentially infinite groups, so long as they had this additional quality that we called squareful. And this was just required to make sure that we could like actually prove this neighbor balance from the terrace. So it did involve us building a terrace sort of infinite sequence and then showing that the neighbor balance at every distance worked. And we ended up needing this property of the group.
Kaethe, are you
to do that.
requiring the group to be countable, or are you allowing your indexing set to be any cardinality?
Good question. It doesn't have to just be countable. So it can be of any size.
So you don't just need, so like, you can't do this for like a direct product of infinitely many Z mod 2s, whatever cardinality of infinite you want there, right? That's kind of what this is saying.
Right,
Or you
yeah.
don't
So
have
however, yeah, I think that, yeah, just the squareful, you mean?
Yeah, sorry, I keep muting myself.
Yeah, yeah. Yeah, and so I guess I say also Kaethe table here because I don't know that like you usually would define a Kaethe table for an infinite group, but in any sense, I mean, it does sort of make sense to define it, and we were able to produce a square that way. So it's kind of nice that the methods from the finite did generalize to the infinite in the context of group-based Vatican squares, is what I would say. But what about, how do we know, like, so what about generating a Vatican square that doesn't come from a group? So actually, in the case of the finite, we don't know whether it's possible to have a Vatican square that doesn't come from a group. So we asked the same question for the infinite. And basically, what we wanted to think about then is how can we even tell if a square is group-based? So if we're just given some box of numbers like this, how would we even know if it's going to be based on a group or if it's given by some Kaethe table? I mean, you don't have to arrange it as nicely as we did, where the, you know, the first column is like the inverse of the first row, and it's all, maybe it's all shuffled around. And for that, you could use something called this, it's called the, what's it called? I suddenly just, the quadrangle criterion. So what you can do is use the quadrangle criterion. And what that says is that for any sort of quadrangle, which I guess is like these three sort of things, for example. So if you have like in the same sort of order and distance, 0, 1, and 2, whenever you see something like that, then there should always be the same thing in that fourth position. So this fails the quadrangle criterion because I have a 3 in this position and a 4 in this one. So the quadrangle criterion is basically a way of telling whether something comes from somehow a Kaethe table or some shift of a Kaethe table. So what we were, oh yeah.
Can you just explain the quadrangle criterion very briefly?
Yeah, I mean, it's, you know, like we could write it down, but I think it's easier to sort of visualize it like this. So whenever you have these sort of 3 numbers arranged in a quadrangle, you might say, right? So as their distance is the same between them, and they're like, you know, one of them is on the corner, like the 0, and then you have 2 in this case at some distance away and 1 at some distance away. So whenever you see a sequence, a sub part of a piece of your square that looks like this, you should always have the same number in the 4th position. So the reason that this fails the quadrangle criterion is because I have different numbers in these positions. And so essentially it's just putting to a mathematical statement the symmetries that we're noticing that come up in these Kaethe tables, where you expect there to be that amount of symmetry. Like here you have the 2 and the 2 and the 1 and 1, and you would expect there to be maybe 0, 0 or the same numbers here. Okay, so using that, which, you know, I don't need to get too into, so just basically starting with this type of square, what we were able to do is then grow it to be an infinite square. Okay, so if we could just start with this bad thing that we knew could not be group-based, then anything that contained it couldn't be group-based. So we were able to grow this into a Vatican square that you can't get just by permuting rows and columns of the Kaethe table. And that's something that we don't know, as I mentioned before, whether you can do that in the finite case. We also were able to produce a Latin square of each infinite order such that no permutation of its rows and columns gives a Vatican or Roman square. So we were also able to produce Latin squares that weren't Vatican and badly weren't that. So these are just sort of two differences that you see from the finite case, where we have a lot more freedom in how we can build these squares since we have the infinite to work with, and we were able to get these results. And there's a lot more results. So there's a lot more stuff in that paper that is there, where we look at semi-Vatican squares, which is also interesting, orthogonal stuff. I mean, there's all sorts of other results in the paper, but the main idea is sort of behind what the problems that I was talking about. So yeah, so I also wanted to spend a little bit of, I'm basically done, but I wanted to spend a little bit of time talking about future work in this direction that if anyone is interested in doing, like students, I think it's very accessible to a lot of people, even if you don't have a lot of background with a lot of the advanced mathematics. I think you can really approach it using these squares and Sudoku puzzles, because the next question that we're working on is thinking about infinite Sudoku. So here's an example of a Sudoku puzzle. This is if once completed, it would be an example of a Latin square. But it has the further requirement that in each of these boxes, every number only appears once. So so often you're given this puzzle and then you have to fill in the rest of the Latin square just based on this information. So when generalizing this to the infinite, we weren't so concerned with the boxes, or at least that's not what we're particularly concerned with right now, is like these boxes. Oops, but what we are concerned with is this concept of partially completing the Latin square, right? Because it's not so easy to just write a Sudoku puzzle. I mean, essentially what you want to do is start with maybe a completed Sudoku grid, a completed one, and then just take stuff away, right, in some fashion. But if you take too much away, then the person may not be able to fill in the whole puzzle. And if you give too much, I mean, you want the puzzle to also be easy to solve, right? So you want basically for there to just be one way of solving the puzzle given this information. So the person playing the puzzle, starts putting these, I mean, does anybody see anything? I mean, we could start doing this puzzle just if you're not familiar with the process. But the question that we're asking for the infinite is more about the designer of the puzzle rather than the player, but it all comes into play. This is, I think, one that I just took from Wikipedia or something. Sorry. Every time I move my mouse. It looks to me like I think,
8 goes in the bottom left middle.
So here, yeah, because you kind of look here, you see that there's already an 8 in this column, there's already an 8 in this column, there's already an 8 in this row. So that leaves the only space where it can be right here, right? And so based on sort of reasoning processes like that, you're supposed to be able to complete this entire square. But it's possible, I mean, if they gave you no entries in a square, then there'd be lots of ways of doing it. So the hope is that when they've given you this exact number of values, that there's just going to be one way of doing it. So we make some definitions, and these are definitions that you can make in the finite case. So we would call like what they give you in a Sudoku puzzle, right? These numbers that partially fill in a square, we would call that a partial Latin square. And that's just a subset of a Latin square, right? And we say that, like, so that's a partial Latin square. Oh yeah, so we call that completable if it's just a subset. It's completable to L if it's just a subset, because you can complete filling the puzzle to get the Latin square from it. And if there's exactly one such Latin square that you can get from that, then it's uniquely completable. And if it's uniquely completable, but no proper subset of P is uniquely completable, so it's not possible that you could have given less information and still have the same square, like it could be that there's a different square, then we call it a critical set. So a nicely designed Sudoku puzzle, like in this previous slide, will be what we would call, would be a critical set. So lots of work has been done in uniquely completable partial Latin squares and critical sets in the finite case. So future work, we want to ask the same questions about the infinite case and see what happens with that. And so I guess I'll leave us, no, gave away the last slide. So I guess I'll leave us with this question, which is this an example of a critical set for that integer square, that infinite Latin square that I showed a few slides back? Does this, where I've just gotten the first, I guess, quadrant 1 and quadrant 3, is that enough information now, first of all, that I uniquely can fill in the rest of the integer square just by deducing where numbers have to go? And I'll leave you with that question. And thank you very much for attending. And that's it.
Let's have a round of applause reactions for our speaker. Thank you very much.
So are there any other questions?
This probably complicates matters a lot, but I suppose Sudoku is supposed to have the property that not only is something completable, but there's a route to complete it. I'm not sure whether that's different, but that there is something, so that there is a first square that you can figure out that it has to be something or other, and then the late, and so forth, so that you can do it step by step. That sounds somehow hard, like it might be harder to achieve than just there exists something if you knew the whole thing.
Right, I think that comes up in this square. I mean, I think we all know there's a way to complete it, so that part's done. We know that this is a partial subset or sub-square of the full Latin square on the integers. So we know that that works, but the question is there only one square that contains this that's also a Latin square? So those are the kinds of questions, and I think the only way that we would know to do that would be to do those kind of paths that you're talking about, like, try to come up with a train of reasoning or a proof that allows you to say, yes, I know that the 0 has to go in the middle, for example, because, you've already covered everything here and you've already covered, et cetera. And so there, I think we can definitely decide, yes, 0 will have to go there, and so on. But the question is, could I have given less information maybe and still have, needed to deduce all of the other numbers? those sorts of things are trickier to ask, but I think that naturally, if we have a logical path to it, then it'll do what you want it to do with that Sudoku puzzle thing, where there should be a path logically to finding it. But yeah, I mean, it's tricky. I mean, sometimes computers can think that it's very easy to fill in the square, the Sudoku, but for a person, it's like way too many levels of guessing and reasoning that you would have to do to figure it out. So that is a good question as well in the infinite case. But I think right now we're just focusing on like our own reasoning, yeah, capabilities. Like that makes sense to us.
But I guess it's an interesting point because, you know, suppose that your square has more than countably many blanks. And then, you know, you fill in the first one and the second one and the third one. And then eventually you'll fill the first countably many and then you'll fill the next one. Or, you know, like you need some way of,
yeah, the
counting.
transfinite induction that has to take place there is definitely more complicated than in the finite case. So yeah, we use a kind of induction argument in all of these things, but for larger and larger sizes of infinity. And yeah, I think it is a good question. I mean, it's even a good question as to how to say, like, I mean, I think we've decided, well, it's a subsquare, but then you might ask, like, what sizes do you have to have of a critical set for the integer square? And I mean, the sizes, it seems like, need to be the same size as the square, basically, but, you know, you're filling in less information. And so then you start talking about, like, well, what do we really mean by having it be less information? Maybe it's like, I don't know. Yeah, I mean, there's all sorts of definitions and arguments to be made here that we're just exploring. I mean, no one, I mean, not that I know of people really looked at this question, because who wants to do an infinite Sudoku puzzle, really, except for set theorists, I guess, and we don't tend to look at this stuff. But you know, that means that there's a lot of sort of
So I have a question,
low fruit. Yeah.
So for this one, you can never get, it looks like you can never get a finite Latin square as a subset, just because of how they're written. And so is that something that you can get in other infinite ones? Like, can you start with a finite one and then extend it?
Yeah, so I mean, I think that typically what ends up happening is that we start with a square, but it's not really in and of itself a Latin square. So for example, here we had all these other numbers that, you know, you normally would want to restrict your index set. So it kind of depends on what you mean by that. I mean, in some sense, if it's all different numbers in every possible place, then in some sense, I guess it does restrict to a Latin square just because it's different symbols. But yeah, you tend to not have that issue where you're going to have the same sort of numbers in a box like this.
But is it possible to start with a Latin square and extend it to an infinite one?
Yeah, I think so. Yeah, I think that should work. The way that we grow these squares, I think that kind of thing can happen. I mean, you can almost think of it as growing it like just by adding things outside of it. You know, like you start with a square and then you can just put something here that doesn't break anything. Put something here that doesn't break anything. And as long as nothing breaks and you can keep going, you're pretty good. But the issue is that you have to prove that nothing sort of broke. And that's really what the argument is. But I think that what you're describing should be fine. I mean, we did it in a slightly different way in the case that we built the Vatican Square, just because we liked building the terrace. But I think you could have just started with the square that you wanted and kept growing it outward that way. Yeah.
And have you looked at things like automorphism groups?
Yeah, those sorts of things did come up, yeah, in the paper for sure. Yeah. But I mean, there may be things that we didn't look at that is interesting in there with groups.
In the finite Vatican square case, is it known that they have to be p minus 1 by p minus 1?
I think there's other examples as well, like if you have like 3 mod 4, so, you know, like there's like some kind of thing where it's like the order of it that you can generate Vatican squares. But that, certainly they do exist for all of these in the way that I said, and then I haven't quite, I don't know that I've looked at it for like other cases, but I think it's a similar methodology.
And do all the constructions use z mod p minus 1 for the Kaethe table, or do they use other groups of order p minus 1?
Right, so I think there might be other examples, but in this, for this result, yeah, they use p minus 1, yeah.
Yeah, just because some of the symmetries of that table are because z mod 4 is abelian, right? And so, but if p is a larger prime, then you know, you might have a non-abelian group of order p minus 1 and kill a lot of the symmetry.
That's a good point. Yeah, so I don't know. Yeah, I haven't looked in too much detail at how that works. So maybe it's that you need more tricks there as well, or maybe that it's a different group. Yeah, I'm not sure.
Do we have one final question for the speaker? Okay, let us thank Kaethe again. Thank you so much.
Thank you.
Thank you.
And
Really...
oh, sorry, go ahead. Yes, thank you so much. And the next first Friday math seminar, you know when it is. It'll be the first Friday of November. So that's November 6th at 4 p.m. So thank you so much for coming, everyone. And we hope to see you again in a month. Thank you again, Kaethe, for a wonderful talk.
Thank you. Bye.